We'll recalculate it.
There we go. All right, everybody, get up so you can see. Battery, right? Okay, it says on here which side's plus and which side's minus.
Okay.
Wait, what?
Okay. I'm good. Lauren, which one's plus?
Outside.
This one.
Which one?
Outside's plus.
The one with the little line by it.
Yeah, the one with that dash.
No,
that
that's
looks kinda like a
negative.
minus sign.
You're messing with me. So the negative one's in the middle, positive one's on the outside. Okay? All right, so which one do you want me to hook up to positive?
Red wire.
Red?
That's positive.
Red to positive.
Negative.
Okay? And I will hook up the yellow or negative. Now what this is I have drinking straws on here just so it's a little easier to see. All right, but what I've done is I just have a long enameled wire in here. Okay, so it's just a wire. All I'm going to do is hook this up straight to the battery. Now if I hook this up straight to the battery, I've shorted out the battery, right?
Yeah.
So it's going to heat up.
So the wire's going to get really hot. It's going to heat up because I'm going to have lots of current, right?
It's going to melt through it.
And it could melt through it, but we're not going to keep it connected forever.
It's gonna explode.
Okay, so if I connect it up, okay, nothing very exciting happens. Ta-da, there you go. Nothing. All right? But I have a whole stack of magnets right here. All right? Stack of magnets. Very exciting.
Oh, crap, my phone.
You got that on tape, you know. All right, so here I am. I'm holding this above this stack of magnets, if I can get it to... There we go.
I say worst things in lab.
All right. You say worst things in lab.
No, but I mean.
Okay, you ready? Shh. You ready?
Ah.
Wait a minute, you see that? Okay, so it's right here. That's because you weren't paying attention. You ready?
Oh.
So electricity goes through it. Now when I have it over here and I connect it, nothing happens, right? When I have it in the magnetic field, right above here, and I connect it, okay, which way does the wire receive a force? To that away, right? To your right. To that away. Okay, now, when I hook this up, this is positive, correct? So positive comes in the red wire, comes down this way, and across this way, and then back up. So my question is this the north or the south end of this stack of batteries?
North. And they're magnets, not batteries.
Did I say batteries? I'm sorry. Magnets. Okay, when I hook it up, they get a force that way. Okay, so the force is that way, and the current is that way. So which way is the magnetic field? Okay, the magnetic field is up, right? Current this way, force that way, so the magnetic field is up. So if the magnetic field is up, then this must be the north side, right? Because magnetic field lines are coming out of the north. Okay, if I flip it over, what should happen now? It should go towards me, I guess, right? All right, let's see. And it does, right?
10 days later.
No, I can't. The wires are getting hot already. All right? So that's a sizable amount of force, right? Okay, we can make this force do things for us. Whoa, hot wire. Hot wire, hot. Okay, there you go. Question like that, very, very likely on the exam. Not that hard, right? All you have to do is use your right-hand rule, okay? And if they ask you to do this on the test, and they'll say, okay, current is going through this wire, the wire receives a force, this way, which way is the magnetic field? And you'll say, up, down, right, left, or whatever. And then they'll say, justify your answer. How do you justify your answer?
Drawing a picture.
Almost. You say, according to the right-hand rule.
Really?
Yes. And that's it. All right, that's all you got to do. Because the right-hand rule is what is dictating you. That's your sign convention, essentially, to figure out which way the forces are. All right? Okay.
Just having a little.
Okay, let's do another one here. Let's see if this other one will work. Sometimes this one works and sometimes it doesn't. All right, where's my hand generator? No, that means you're powering up your binder.
Yes.
All right. Here, let's do it right here. Ian, can I kick you out?
All right.
He's used to that.
Evicted.
Where do you want to
in front of
go?
the camera.
Here, I want to go. I want to go to Hawaii.
There we go.
Here. The next question.
I want to go to Hawaii. That's where I want to go.
Okay, let's see if this works. You ready? Oh. Ah! It won't go the other way. It'll go that way.
I think the table's
Can you
just
see?
set.
I think the table's slanted.
Stuff.
See, it has the right-hand rule on it.
Yes, it does. All right, you ready? Up.
It stops. Once it
No, no,
starts
no.
moving, it
I
doesn't go
think
the
it's
other way.
stuck.
Catch it. Oh, you should try to
You're
stop it
supposed to
right at the
rewind
end.
And make sure it doesn't fall off.
I bet you can't do it. I bet you can do it.
Let's get
Sometimes.
let's get the battery and flip the thing.
Stop.
Oh, let's get it right in. Let's get it right in. Let's get it right in. Reel it in. Reel it in.
To the end, to the end, to the end, to the end.
Oh, close. You got close.
Awesome. All right. Now. Okay, let's do this. Okay, when I go this way. All right, when I go this way. Okay. When I rotate it to me, clockwise, to you that would be counterclockwise, right? So when I rotate this counterclockwise to your eyes,
It's that.
this gets a force which way? That way. The force is that way. Now this says that when I rotate it this direction, the top is positive. The top is the silver wire. That's this one right here. So this is my positive side. Current goes down here, across, and then back this way. You see that? Current goes down this way, through this little bar, and back this way. So the current is this way. The force is that way. So which way is my magnetic field coming out of this board? Okay, force this way, current that way. So magnetic field up again, right? Okay. All right. If you can do those types of, well, thought processes and figure out the direction of the relationship between force, current, and magnetic field, and you can do that for charges as well, then you should be good to go for about a third of the questions on the AP exam. Okay? All right, so let's talk about some of the other questions that you'll see on the AP
What is
exam.
a pizza?
And I put a compass right here. Okay? If I put a compass right here, right next to it. Actually, you know what? Let's do it this way. Make it easy. We'll put the compass on top of the wire.
Is this a spherical compass?
It's a compass like this. So what I do is I have the wire. The wire's like this, and I stick the compass on top of it. Okay? All right, now pay attention, everybody.
Oh, it's on the wire?
Yeah, so it's like this. The wire's down here, and the compass is sitting right on top of it. Okay? And let's say that the compass was originally pointing this way towards north. Say north is that way. When I close the switch to make this all right? When I close the switch to make the current go, and the current will go to the right up here, which way is that compass going to deflect, or will it do anything? Will the compass rotate more clockwise, or will it rotate more counterclockwise? Okay?
Yeah, no idea. It will turn more clockwise.
Let's work our way through it. Okay, let's go all the way back. Here's the Earth. Okay, if you have a compass right here along the equator, the compass points this way.
It's like a Pokeball.
With the arrow.
Okay? The arrow points towards
North.
geographic north, which is actually what?
A south.
Polar south. Okay?
Not this particular theory.
Okay, here's why.
You say, oh,
Because
not this.
the magnetic field lines would come out and go this way, right?
I put her as like, you say, yeah, it's true, but it's not.
Yes.
Okay? Alright, so are you watching?
Yes.
If the compass points this way, then which way is the magnetic field going? It's also going that way, right? It aligns itself with the magnetic field, because the magnetic field lines are going past the compass towards this side, right? Does that make sense?
That'll be slightly.
Okay, so here's my question.
Power is just one.
This is a three-dimensional thing, right? So here's my wire. If this is my wire, and I have the current coming out, and I set the compass on top of it, okay? Compass sets on top. So I'm looking at it from this side, okay? Which way is the magnetic field around the wire?
Currents this way.
Current's this way, or current's this way. So the magnetic field is circulating.
That.
This is
Counterclockwise.
in blue. It's circulating around this way, right?
Yeah.
If you want to say a car,
Like that, right?
Yeah, we're doing that
a
right.
company like,
That
where you
will-
want to say that.
Okay,
cars
hey.
go faster.
Come on. Current's this way. So the magnetic field in the region of the compass is coming across it like this, right? Does that make sense? This is a pretty hard question. Okay, so it comes across the top of it, right? So which way will the compass deflect?
Down.
It's going to deflect this way, right?
Do we know how much though? Or no?
It depends on the addition of the magnetic field that I'm creating here and the magnetic field of the Earth.
Okay.
Whatever the net direction of that is. So like for instance, if the Earth's magnetic field is this way, and I create a magnetic field from my wire this way, then what I'll get is a vector this way, and then a vector this way. Magnetic field Earth, magnetic field current, and that will be the resulting magnetic field total, and that's the way it'll point, is the total magnetic
But
field.
the magnetic field of the Earth has a greater influence on that because it's much larger, right?
No.
The magnetic field of which is larger?
Of the Earth.
It depends on how much current I have going through the wire and how close I am to the current. With this information, I didn't give you enough information to know for sure. But we would know that it would, if the magnetic field goes this way, then it would turn, deflect this way, right?
Is it so strong we like to a straight circle?
If it's a strong, no, it won't go in a circle. It'll align itself. Now, it might shoot past and oscillate a little bit. Okay? All right. So, the magnet will point in the direction of the magnetic field. I mean, the compass will point in the direction of the magnetic field. Okay? And then whatever those two add up to be, that's your total. Okay? And that's the total direction. Okay, here we go. First things first. We will start with a little device right here.
Triangle.
It's a capacitor. But this capacitor has a pointy edge on it right here.
That's not nice.
And this one over here has a hole in it. Okay?
Wait, what is that?
It's a capacitor
Some strange.
where this is the negative and this is the positive. Actually, I should have let you figure that out. But then I take this plate and I make it all pointy and then I punch a hole in that plate. Okay, here's why. Okay? If I get this to a high enough potential difference, then the pointy spot right here is where charge will tend to jump off. Okay?
More direct, more straight.
Well, and the pointier it is, the easier it is for the charges to jump off. That's why, like on a Van de Graaff like this, it's nice and smooth, right? High voltage devices are nice and smooth because if they have any sharp edges, then the charges will jump off. Okay?
Suicide.
All right, so here we go.
make a bring it.
Here's our first thing. Why don't we make this, I don't know. Gonna make it 10,000 volts, okay?
Say 17.
10,000 volts. I don't know. It's gonna be pretty high for the electrons to jump off. I'm making up a number, all right?
One.
We're gonna say the distance between here and here is, I don't know. What do you want it to be?
Half a meter.
Okay, 10 centimeters.
Ain't going.
Excellent. Suggestion?
Half a meter.
Half a meter, so 10 centimeters. Excellent. All right, so we'll make it 10 centimeters. All right, here's what I want to
How
know.
separated are the plates, though? Does that even matter?
How separated are the plates?
Yeah, how big of the hole you
Okay,
punched in?
here's what's going to happen is this little electron is going to jump off of here, and it's going to do what?
Shoots one of them.
It's going to shoot towards this way, and if these are centered, it's going to shoot right through the hole. Okay? It's going to shoot right through the hole.
My hole wasn't aligned with that arrow.
Oh, wow.
Why didn't you tell me something?
I'm sorry. Okay, now you can redo it.
It's an awesome line.
Okay, so here's my question. Is how fast will the electron be going when it reaches right here? Or how fast will it exit? Velocity exit.
So that's the positive plate, right? That's placed.
Very good. Okay, so several things we need to know. Number one is this is my positive plate. This is my negative plate over here. Okay?
Okay.
And I want to know how fast it's going to go when it exits here. All right, now,
Very.
stop. Think. Kinematics, forces, and acceleration, like F equals ma. Energy, or energy and work, or momentum and impulse. Those are our four major tools, right? Because we don't have any springs going on. We don't have any circular motion thing going on, right? So those are really pretty much it. So my question is which one of those four tools do you want to get out of your tool belt or toolbox and start to work on this with?
Energy.
We have a vote for energy. Do we have a vote for anything else?
Minority count.
What? What's your suggestion? Forces? All right. Now, let's try both. We'll try energy and we'll try forces. Energy was suggested first, so let's try energy.
You told me to stop and I froze, and then you never said go. So I understand.
Why are you talking? I told you to stop. That's pretty good. He's frozen. All right. So, what kind of energy do I start with?
Electric energy.
Electric energy? What's electric energy?
Well,
Yeah, but
potential.
Okay, whoa, back up. Do we have conservation of energy? Yes or no?
Oh, yeah.
maybe.
You can't violate that, right?
Okay. What are the forces acting on this charge?
Electric.
Electric?
Awesome and awesome.
Should we worry about gravity?
Not really.
Probably not. The electric force is probably going to be so great that it won't make much difference. Plus the mass of an electron is so small compared to its charge, probably we're not going to have to worry about it, right? Okay. All right. All right, let's do energy then. What kind of energy do I begin with, since we're assuming conservation of energy? We have, what kind of potential?
Electric.
Electric potential over here. What kind of energy would I have here?
Kinetic.
Kinetic.
Kinetic. Will I have any electric potential energy left once I reach this plate?
Zero.
Yeah, very little, right? In fact, if we can call that our zero spot, right?
Not in physics B.
All right? So right here, from location number 1 to location number 2, I can set these equal. All right? Well, kinetic energy is easy. What's our equation for kinetic energy?
1/2 mv squared.
1/2 mv squared. Okay, what's our equation for electric potential energy?
For a charge, KQ.
KC.
No, that's not. We have a charge.
Potential?
All right.
C squared.
Somebody tell me why I can't use.
VQ.
Oops.
Let's go with VQ.
Over R.
We don't have R. Let's move on.
It's not a circle radius.
R is changing.
Someone
And
needs
it's
to call moved on.
Okay. Yeah. We don't have a radial geometry problem, do we?
Yeah, they were laughing.
Shh.
I was like, that's a big-
Hey,
Oh.
you're gonna need to know how to do this on an exam.
Because it's not circular.
We don't have a spherical charge distribution, right?
Correct.
Yeah.
Drat. So how else do I find electric potential energy?
QV.
QV.
Say that again?
KQ1, Q2 overall.
But I don't have radial geometry still, right?
Just QV.
Hey! Because electric potential is electric potential energy divided by Q, right? So electric potential energy would be VQ, right?
Yes.
Alright, so it's just VQ. Alright, now let's see if we know these things. Do we know V?
Yeah.
Yes, we do.
Because the battery and the capacitor, once the capacitor is fully charged, should have the same voltage,
Can
right?
you make
Yeah.
that big Q? Because that kind of confuses me. Over there where you be.
Oh, I don't care. Well, here, let's do it this way. What's V? 10,000 volts, right? What's Q?
Charge of electron.
Charge of my electron, right?
Negative 1.6.
Negative. Oh, do I need to worry about the negative?
No.
No, because I'm just doing this energy turns to energy, right?
Energy
So-
scale of
1.6 e to the negative
19.
19 coulombs, all right? So 1/2 I know. What's the mass?
It's almost
Yeah. The answer is, I don't know off the top of my head. I better look it up on my constant sheet.
Yeah, 7 for 10 flip for
You said
electrician
negative
pipe.
27.
911 to
Nope.
negative 31.
31.
9.1 e to the negative 31st kilograms. That's the mass of an electron. You know what? You might memorize that after you use it a few times. When we get to modern physics, we talk about the nucleus and the atoms and all that. You'll probably memorize that. But for right now, it may not be in your brain. Just look it up. And what's little v? Little v is the velocity we're looking for.
Yeah.
All right, so let's solve it. Okay, will you solve it? What is v? What's the v of my electron? That's velocity. Very good. That's small v. You got to be careful. Difference between big V and little v. All right. I think we get something rather large, do we not?
5.9 e to the 7th.
E to the 7th meters per second. Yikes. Does that break physics, or are we okay?
It's good.
We're okay.
What would be breaking physics? Speed of light, right? Okay, speed of light is 3e8. That's pretty fast, and we can easily get an electron to this speed. Easily. Now, once we get up to this speed, though, in the real world, I just made this problem up, okay? But in the real world, we would have some issues when we get up to speeds of around the 10th the speed of light and higher. We start to run into relativistic effects, okay? We'll assume our relativistic effects are small. You ready?
Yes.
Next thing is it shoots into a region
There's another capacitor.
of another capacitor.
With magnetic
I
field.
have to move my freaking.
Ah, no joke.
Here, let's do it the other way.
No,
Since we're in,
drew that.
you just drew that? All right, we can do it this way. I don't care.
And it's all in free fall.
No, no free fall.
And rotating about.
There's a magnetic field.
All right?
There's 4.
And the electron curves this way. Okay. Which way is the electric field? Draw the electric field between those plates. You might want to do it in pencil, just in case.
Too late.
Are you playing that we're not perfect?
Which way is the electric field between those plates?
Down.
But it's going up.
Doesn't matter because it's an electron.
Ah, it's an electron.
Bad machine.
Just
All right. So our electric field is this way.
Because it tells a positive move off negative because the electron went.
Because that's a negative charge, and so it will receive a force up. So it receives an electric force up. Okay? So it moves upward. Okay,
That's an electron.
now, let's say that it is hooked up to, this one is hooked up to a battery.
Let's say there was a hole. What is the speed of it now?
Hang on. So here's my battery. So which side is the plus side?
The top one.
The top.
Top one. The top one is the plus side. The bottom one is the minus side. And if you had trouble figuring out which way is the electric field, just think this. It's an electron. Which plate would it be attracted to? Positive. Okay, so that's positive, that's negative, and then my electric field is down, right? So you can always think of it that way if you wish. So there's my plus side, and there's my minus side. Let's say that this battery has a EMF of 100 volts. Okay?
Agreed.
All right. Actually, you know what? You want to make it bigger than that?
No. No, we meant like for us on our paper.
101.
Let's. Okay, we'll just leave it 100 volts. I wrote it down. I'm just making numbers up. 100 volts. Okay. Let's say the distance between the plates. Colin, what did you say the distance between the plates was?
2 meters. I didn't say anything.
Half a meter.
Excellent. 1/2 of a meter. 0.5. All right. Hi, Colin. All right. Tell me, what's the electric field strength between the plates? Hey, give yourself lots of room because it's going to keep going. So it's going to go. I'm going to go to right here. Okay, how do I find the electric field strength?
V equals ED.
All right.
I don't know.
V equals ed, or the electric field equals negative V over D. Now remember, we have taken the absolute value of this, right? We will worry about the negative sign when we get to physics C. All right? It has to do with electric potential energy and electric forces, which we'll talk about later. Okay? So it's just V over D. So it's 100 divided by 0.5, which gives us 200 newtons per coulomb, or you could say 200 volts per meter. Either way, it's the same thing. Okay? Hey, what is the acceleration of my electron?
A number.
We can calculate force and then just
Ah.
acceleration.
The acceleration of my electron would be F equals ma, but that's an electric force, right? Equals ma. How big is my electric force?
Depending on your
Can I use 1 over, or can I use KQQ over R squared right here to find electric force?
No, it is not radius.
Because I don't have radial geometry, so what do I use instead?
the V is F over Q.
What's that? E equals F over Q, or F equals
EQ.
EQ. So I got EQ equals MA. So what's my electric field strength?
200 volts.
200 volts per meter. What's my charge? Ooh, no. Oh yeah, that's right. 1.6 e to the negative 19th coulomb. Sorry, I got confused for a second. What's my mass? 9.1 e to the negative 31st kilograms. And then that's my acceleration. So what is my acceleration of this thing? Some number, probably a large number. Because I'm divided by negative 31st power. So that's going to be really big. Right?
3.5 e to the 13 meters per second.
3.5 e to the what? 13th?
Positive 15.
Positive 13th. Meters per second squared. Okay, now that looks like that breaks physics, right?
No.
But remember, yeah, acceleration just tells us how the velocity changes with time, right? So is it possible to have an acceleration greater than greater than 3e8?
Yes.
Yes. It's just not going to be able to do that for more than a second, right?
It's probably going to be half, not even half a second.
Yeah, this electron would slam into this plus plate very quickly, right? Very, very quickly. All right? with that acceleration, could we figure out its trajectory path?
No.
We could, because that would be like our G
Will we?
in our normal trajectory problem, right? But that would be huge. Okay, we won't do that this time. All right, here's my next question. I don't want it to curve up. What I want it to do
Just go straight.
is I want it to go straight right through this hole in this plate.
Too
You
bad.
need a force.
No.
So I need a, who said it? So Melanie, I need a magnetic field. Here's my question. Which way is the magnetic field to make my electron go straight?
It should. I'm sorry.
Okay, you want the velocity to go this way. So
Okay, think about it in steps. In order for something to go straight and not turn, what must be true of the forces? Yeah. The forces must cancel. So, I need what kind of force this way? A magnetic force. Okay, now that you know the magnetic force is this way, and the electron is traveling
that or way.
that way,
Field has to be this or way.
which way is the magnetic field? Okay, everybody,
This or way.
shh, don't tell me. Discuss it with your neighbor. All right, Ian asked a very good question. Ian asked,
Are those two more plates?
what was the question? The question was, what's the direction of the magnetic field that I need to apply so that my electron goes straight through and doesn't curve at all?
Velocity.
Do I
Force
use
has to still go down.
my positive hand rule or my negative hand rule?
Negative hand.
Okay, I use my left hand rule. Okay. BIF, BIF, or BVF, right? For my current velocity. Yeah, it's like current, BIF. I always say BIF, but I is the current, right? And our current is that way, right?
Or velocity.
Or velocity. So BIF or BVF. Okay, velocity's this way. Force is down. So B field has to be
That or way.
into the board.
But we want it different.
So it will go straight
Like this.
through. Okay, now that's the kind of question they'd ask, and I think it's asked in your e-homework in some form or fashion. I think they ask which way is the electric field instead. We ask which way is the magnetic field, okay? So it's just the opposite type question. But remember, these two forces must cancel.
Will it ask for a value?
All right, so the next question is how, hey, how big is the magnetic field that I would need?
It's going to have to be equal to
Equal to FH.
Okay, so magnetic force equals electric force, they must cancel. Electric force is just EQ, right? Magnetic force is?
Mu naught over 2 pi times I
negative
over
2e7.
Oh, but we have velocity, so it's that other equation.
Oh, yeah. Sine theta. I remember that. Sine theta.
There is a sine theta,
QVB.
Q.
Oh, whatever. QVB.
QVB or BVQ, however you want to say it. Okay? Because that's our force equation, right? Some of you were saying the mu naught over 2 pi, that's the magnetic field equation, right?
Yeah, that's
All right. Okay, and then what happens? What about our sine theta? See, it's going that way, but the magnetic field's into the board. So that's 90. Sine of 90 is 1. And my q's go away. So my magnetic field would just be E divided by V, right? So what's my electric field strength? 200, right? Volts per meter divided by... Now, which V is this? Is this...
Velocity of the electron.
That's the velocities. That's small v, right? So the velocity of my electron is quite large.
5.93.
5.9 E7 meters per second. Okay, yes ma'am.
If there's acceleration, why doesn't the velocity change?
No, it's acceleration.
Excellent question. That's a great question. Melanie asked, if we have an acceleration, why am I still using the same velocity? Okay, this velocity was the velocity that exited here and entered here. And before we put the magnetic field in, it would accelerate up at that rate. But then we put the magnetic field in and it goes straight. So now my acceleration is 0 because I put the magnetic field in. Does that help out? Okay.
Yes.
That's an excellent question. That's an excellent question. All right, so we get a very small magnetic field. What's our very small magnetic field? What was the first number? 3.4 e to the negative 6. Oh, units.
Tesla.
Micro. Oh.
Tesla. Or you could say 3.4 micro Teslas, if you'd like. All right. Wow. Are we done with that project? Hey, guess what? We're not done. Ah! What do you want to happen? I mean, for a shark that comes by.
Down here. No, you can-
All right, here's the next thing that happens. This magnetic field is the same magnetic field we have over here.
Oh no. Come on. What are you doing to us?
All right? Question number 1. This magnetic field is the same magnetic field. All right? Question number 1. The electron comes out. Which way, or sketch its path, please. This device is called a mass spectrometer. And what a mass spectrometer does is you can take an unknown object, charge it up, shoot it through a capacitor plate, through a crossed electric and magnetic field, and then into a magnetic field, and measure its path. And from that you can find the charge to mass ratio of that object. Okay? Now, why would you ever want to do that? Well, in chemistry you might want to do that to figure out what it is. But where do they use that in the real world? Here's one example of where they use it in the real world. Forensic science. Okay? Let's say that you've got somebody has some unknown material in their body. It's poisoning them, and you want to find out what it is.
Data point. Ringworm.
Ringworm. So how do you find out what it is? Or let's say that you work for the police department. Yeah, you work for the police department. In the police department, there's an arson, and you want to find out, well, what it was that started the fire. You just scrape up the area where the fire began, and you put it in this device. You heat it up. Actually, they put it in a can. They heat it up to get gas to come off of it. They send the gas through here and charge it up and shoot it through and find out its charge to mass ratio. They got a whole list of charge to mass ratios for all sorts of things. And they can find out whether it's kerosene, or if you're a doctor, whether it's arsenic or whatever it is that's poisoning you, right? So it's a detection device for what they can put charged particles in, or make charged particles, and discover what that atom or molecule is. Okay? So that's a practical use for this. All right?
I'm glad the computer does all
Now that we know that, let's find out whether you've been poisoned with arsenic or
Milk.
yeah, or whether you're just lactose intolerant. All right. So through here comes our charged particle. Which way does it go? If they ask you to draw the path, which way will it curve?
Parabolic down.
Okay. Right-hand rule or left-hand rule? Left. Okay, so it goes through B field into the board, so it's going to curve down. It's going to take this path. Okay?
So why would it circle down? Because it's an electron? Or
Okay.
how do you determine if
How do we-
It's the force down, right? And that's like.
because it continues going, right?
Centripetal thing?
Yes. Okay, so what happens is the reason why it goes in a circle and not a parabola is because the velocity is this way and it turns, and as it turns, the force vector turns with your, in this case, left-hand rule, right? So the force is always towards the center. That's why you get circular motion.
So it's always, if it's any charge, any magnitude, any mass would always do circular or not always?
If it's in a magnetic field
Like
and it
if
has a
it's-
charge.
If the magnetic field large enough to make it make a half circle, it would. If it's too short, it wouldn't go all the
Well,
way.
that's correct. Yeah, it'll exit somewhere. Okay. In fact, in this device, what they'll do is they'll have a detector over here. And it's like, well, where's the detector? The detector, the diameter, or this distance from here to here, of where the detector is they use that information to figure out the radius of the circle and work backwards. Yes, ma'am?
Our
So,
grades up
like,
there.
if it was big enough for it to do a complete circle, would it go on the same circle with the same radius, or get smaller like a spiral?
Okay, I had a great question. Lauren asked, okay, if the magnetic field is large enough and it shoots in, and it shoots in and it goes into the magnetic field and it's large enough, would it travel the same circle the whole time? The answer is yes, it'll travel the same circle forever if it doesn't gain energy or lose energy. If it loses energy, it will slow down. As it slows down, it will spiral in.
How would it lose that?
Well, like if it hits another particle, things like that. If you give it energy, it will spiral out. Okay? Our first particle accelerator was this type, where it was called a cyclotron. Okay? We'll talk about that in just a second. All right, here's my next question then. It comes around here and hits here. What's this distance?
That's a number that.
Half a meter.
Okay. F equals ma. I'm going in a circle, right? So what's my force causing me to go in a circle?
Force B field.
This same force, right? So QVB sine theta equals mv squared over r, right?
Yes.
Okay, a couple things happen.
The V's go away. Well, one of them.
One of the v's goes away. My sine theta is still 90, right? So that gives me 1. So I'm left with QB equals mv squared over r. I'm sorry, v over r. Okay, what am I looking for?
R.
I'm looking for r, and then I'm going to double it to give me x, right? In my diagram. So r equals mv over qb. Okay, what's m? That's the mass of my electron. 9.1 e to the negative 31st kilograms.
Oh my God, this
My
is crazy.
v is my velocity of my object, which was 5.9 e to the 7th meters per second. My charge is the charge of my electron, 1.6 e to the negative 19th coulombs. And my B is my magnetic field, which is 3.4 e to the negative 6 teslas.
98. Times 2.
We get a ridiculously large number here, don't we?
Yeah, 197 for the total distance.
100. Oh, what's the radius?
98.7.
98.7 meters, right? 98.7.
That's what I say.
So x is twice that. What is it? So it's 190 what?
7.4.
7.4 meters.
Right.
All right. So the random numbers I picked gives me something that's rather large, right? In a real mass spectrometer, it's a device that can sit on a table, and so they would have a much higher. Well, they'd have a much higher magnetic field, probably, or a lower velocity. Okay? All right. So there's my radius. Oh, no. How long does it take to get from here to here?
Okay, well, we know velocity, we know the distance it has to travel by
Kinematics. We know the velocity it has, and we know
the circumference.
half the circumference, right? So
Just V over time.
velocity equals
Assuming it's a constant velocity.
Assuming a constant velocity. So my time just equals my distance over v. That's
Getting little purple
2 pi r divided by 2. That's my half circumference. Divided by my velocity, right? Which was 5.9 e to the 7th meters per second. That's going to be a really short time, isn't it?
0.000.
Wait, pi r, so r
R
is
is 98.7. What do we get?
5.3 e to the negative 6.
5.3 e to the negative 6 seconds. That's pretty quick.
Isn't it just pi r over 5.9?
Yeah.
Yeah.
It's
Pi
not-
r.
Did you use x or r? 5.3 e.
I'm sorry. My x,
Oh, yeah.
my x was change in distance over velocity. So that x, sorry, that should be half the circumference. 2 pi r divided by 2, so just pi r. That's correct. Could we have asked this in different order?
Yeah.
You bet.
They make us go reverse.
They could have gone in reverse. They could have said the charged particle goes this way in a magnetic field. What's the sign of the charged particle? Positive or negative? Justify your answer. So here, let me give you one like that. Here's my magnetic field.
Stop.
Hey, come on. Here's my charged particle. It goes through and it turns this way like that. Okay? It was going to the right. Okay, tell me, is the charged particle positive or negative? Justify your answer. Okay, what's the sign of this charge?
Positive.
How do you know?
Because it's going the right way on the right hand rule.
Because my right hand rule says it's going this way, and my magnetic field is out, and my thumb said it should get a force down, and this one looks like it's getting a force down, so that would mean it follows the right hand rule, and is the opposite of the left hand rule, right? Alright, so there are lots and lots of ways they can ask this particular question.
And it gives us a velocity when it's positive, so we know it's negative.
Okay? They can give you parts of it, or all of it, or whatever. So, that's the majority of your homework. Now,
I'm not. The equations next.
we have one more part to electricity and, magnetism. Okay? One more part. Alright, now remember, what year was it? 1820, that Ørsted discovered that, by accident, a wire produces a magnetic field. Okay? So wait a minute. Here was the big question then. If moving charge in a wire can produce a magnetic field, can a magnetic field produce moving charge or a current? And everybody thought by symmetry this should be true, right? It seems to make sense, right? If moving charges produce a magnetic field, then a magnetic field ought to be able to produce moving charges. All right, well, it took them 11 years. Okay? 11 years to get this to happen. But they eventually got it to work. It took 11 years because they didn't know what they were doing. They were starting from scratch, right? And so they had a lot of theories, a lot of false starts. They would be able to generate some current, but they couldn't figure out why it worked or when it worked. Okay? Until finally in 1831. Okay, 1831, everybody. This is like, what, 20 years before the Civil War. All right? Michael Faraday is the one that gets credit for this. There was actually 2 others that were working on it as well. Excuse me, the Russian Heinrich Lenz, and the American Joseph Henry. Okay? There's debate about which one of them actually came up with it first. Common thought now is that perhaps Joseph Henry actually discovered it first, but did not publish his work. So Faraday gets the credit for it. So, anyway.
So the unit would be called a Henry?
Yeah, it would have been called, well, there is a unit called a Henry. So Henry still got some credit. All right, let me show you what Faraday discovered. Okay, let me show you what Faraday discovered. Okay, Faraday discovered that in order, in fact, let me read it to you. Okay, you ready? Take notes. Faraday came up with this. It's called Faraday's Law. You ready?
Okay, all done. I need to write that.
Okay, it's going to sound really weird, but just write it down. It's called Faraday's Law. Here it comes. The induced EMF. How do you spell EMF? E-M-F. M. The induced EMF in a loop is proportional to. The induced EMF in a loop is proportional to the rate change of magnetic flux just making words up.
I think so.
The rate change of magnetic flux through the coil. Yeah, it's a conducting coil. All right? All right. Let me read it again. The induced EMF in a loop is proportional to the rate change of magnetic flux through the coil. All right?
What does that mean?
Exactly. What the heck does that mean? All right? I'm going to show you this in a second, since you asked me that question first. Okay, which words in that sentence do you not understand? Flux.
Magnetic.
Okay. The biggie is magnetic flux and perhaps induced.
Yes.
Okay? All right, so let's talk about what flux is. Okay, flux is a vector Flux is a vector that passes through an area. Okay?
But a vector of what?
Flux. Okay. Any vector. Now, if you want magnetic flux, then what would the vector be? A magnetic field vector. Okay?
Oh, so it's of anything?
Yes. So you could have, we have electric flux, we have magnetic flux, we have gravitational flux, there's all kinds of flux. And we have the flux capacitor, of course. All right, now, which way is north? Does anyone know?
You mean
That way.
it's that north pole?
I think it's this way, isn't it? Okay, let's assume this is north. Okay, if
That way.
I assume that way
is it this way?
The front of the school is this way, and the front of the school is south. North is that way.
Okay, north is this way.
No, it's not. It's that.
All right,
I have mixed up.
we'll make life easy. North is this way.
It's probably that.
Okay? So this is the north wall. That's the south wall. East, west wall, ceiling, floor. Now, everybody, which way is the Earth's magnetic field pointing then?
South.
Field? Well, because if the field's moving that way,
That way, right?
field is going that
To
way.
the South Pole.
Towards the south.
To the south magnetic pole, towards the north pole, right? Okay, so the Earth's magnetic field goes this way. All right, which walls in this room have flux?
A vector going through it.
A vector going through an area.
And south.
The north and south.
That one and that one. All right, so the back wall and the front wall. Does everybody see that if the vectors of the Earth's magnetic field are pointing this way, you see that they go by the ceiling, but not through the ceiling? They go by the side walls and the floor, but not through them. Does that make sense?
Yeah.
Okay, that's key. Because this is, put that down.
You're just showing vectors going parallel.
All right, now, if the vectors go by, above, below, by, but not through,
Flex.
you have no flux. Okay, if the area is at an angle and the vectors are going through at an angle, all right, we have partial flux, but not maximum flux.
Max flux has to be a 90-degree angle.
Max flux, actually, because of the way they designate the angle, it's a little weird. But let me show you. Okay, we have partial flux here. Now, here's our equation for flux. Our equation for flux, for magnetic flux, is, here's our symbol for magnetic flux. Now, you might see it like this with a B. You might see it like this with an M. Check the equation sheet that they have now. Which one do they have? Look in the bottom of the electricity and magnetism part. They have an M? Okay. I will try to write M, but you will see some books that will have B. So if I write it B, then just forgive me. Remind me to make it an M so it's the same as on your equation sheet. Okay. Magnetic flux is BA cosine theta.
Area and field.
All right. So B is magnetic field, right? B equals magnetic field in Teslas. A obviously equals, no, it's on our next homework. Area. Okay, what's theta equal? Theta is always the angle between two vectors, right? In this equation. But here's our problem. That means that B, magnetic field, is obviously a vector, right?
How can area be a vector?
Excellent question. How the heck can an area be a vector? Okay, here's how they do it mathematically. Do you see this board? Do you see that I can put a vector in the board like this, or like this, or like this? I can put an infinite number of vectors in the board, right? But how many vectors can I make perpendicular?
1, 2.
Technically two.
One that
This
way and
one
one this way.
or this way. Okay, so to have a unique vector to represent an area, they say that the area vector is perpendicular to the area itself, okay? Now, you could either have it come this way or this way. If it's a closed surface, it always points outward. So like if this room was our closed surface, then the area vector for the ceiling would point up, and the area vector for the floor would point down. Does that make sense? So it points out of the box. Okay? We don't really care at this point which way it points, as long as you say, no, it's perpendicular. So watch this. This is why this makes sense. You see that my electric field vector, my magnetic field vector is this way? Which way is my area vector for this?
Down. Up.
Down or up, either one. But you see that it's perpendicular either way? What's the cosine of 90?
0.
Hey, so right here my flux is 0. Right here, which way is my area vector? I'm going to make it this way, so my angle is smaller. My area vector is perpendicular to my surface. My area vector and my B field vector have an angle between them of 0. Cosine of 0 equals 1, so I have maximum flux. Now look over here. If my area vector is perpendicular, say that way, perpendicular to my surface, and my B field vector is going this way, do you see I'm going to get an angle between 0 and 90, or not 0 or 90? Put it that way, right? So I'm going to get a cosine theta that's going to be between 0 and 1. I'll get partial flux, right? That make sense?
Yes.
Okay, here's the deal. This is what flux is. What did Faraday say has to happen? Number one is, let's read it word by word. It says, the induced EMF. Okay, what's an EMF?
Electromotive force.
EMF is electromotive force. It's like a battery. So induced, listen, induced EMF means that it's like a virtual battery. It's a battery that's made even though there's not a battery there. It's an EMF, as if a battery is there. In a loop, what does a loop mean? You've got to have a complete circuit. It can be square, doesn't have to be a loop, but it could be square, doesn't have to be circular. Okay? So this is proportional to the rate change of magnetic flux through the coil. So, wait a minute, this is magnetic flux. How do you do rate change?
Delta T.
Magnetic flux over time. So if you can change the flux with time, you'll produce a virtual battery in the loop, and it will produce current.
Okay. That's what you meant by it.
Okay? Now, that means that my magnetic field that passes through this loop, I have to change this with time. So what does that mean? I've got to change BA cosine theta with time. All right? Now, back to this. Back to the incredible device of the future, an overhead.
This is more overhead than that.
No, you don't need to turn off the lights. You can see this, right?
Mr. Bruin,
Turn off the front light
Mr.
then.
Bruin, you hear what I said?
What?
That's more overhead than that.
It's a projector.
Try the other one.
Very nice.
That'll work. We got enough light here to see. Okay, now, you see this? What's this?
Magnet.
And what else does it make?
Makes a magnetic
Well,
field.
you see a magnetic field coming out of here, right? Because you have your magnetic field glasses on? All right, magnetic field exits the north and then enters back in the south, right? And then comes through, all right? Okay, you see these? These are coils, loops of wire. Okay, now I have to somehow or another get a magnetic field through the loop, and then I have to change one of these at least with time. And if I do that, I'll produce a virtual battery, which will produce a current. Okay, so tell me, how can I take this next to one of these loops and change one of those with time? What can I do?
Put it in.
I could start out here and then get closer, right? Because what am I changing? B, A, or cosine theta?
B.
Changing B. So I'm changing B. It's getting stronger, right? Okay. Could I
change coils?
Ooh, to change A, I'm going to have to change the shape of this coil, right? Okay, now I'm not able to do that because it's wrapped around plastic. So I can't do that. How can I change theta?
Spin it.
Yeah, I could spin this, right? All right, so let's
What
see.
if you change the how big the coil is?
You could do that. You could change the shape or size of the
That
coil.
changes the area, right?
Yeah, that would change it as well. Now, by the way, everybody, you notice that each one of these coils is the same exact area, but this wire is looped around many more times. So this one has less area than that one, and this one has the most, because this one is like, if it has 100 coils, then it has 100 areas. Does that make sense?
It's a volume.
You need 100 areas. Oh my god.
All right, so
Dimension is this?
here you go. So move it closer, right? See the current? Oh,
Hitting
Oh,
it
you
back,
missed
Mr. Bruin.
Oh my god.
come on. All right. What if I move it back and forth?
It goes down.
That does it too. What if I spin it? That does it too, right? At least it wiggles a little bit,
Now try it
right?
with the south side.
South side? All right, south side. Hey, south side approaching. Which way does it go as it approaches?
Opposite of
This way? All right, so it's going this way. North side approaching. Which way does it go?
Yeah.
the other
It
way.
oops. It goes that way, right? Oh my gosh. That's going to be one of the big questions on the exam. Is if I have a loop of wire and I have a magnet and I bring it close, which way is the current going to go? All right. So, we'll figure that out.
So field would be
Please
this
just
way.
kill the boxes.
By the way, you see this? You see how much that one moves? See how much that one moves? How much that one moves? Okay, why does this big one move the most?
More areas.
Because it has the most overall area, because it has more areas, so therefore more flux, therefore more EMF, therefore more current in the loop. Okay? All right. Questions?
You killed them.
All right. Yes, excellent question. Melanie asked, all right, so what if I had a loop of wire that was like this, and my loop was 10 centimeters by 10 centimeters? First of all, be careful. The area would be 0.1 meter times 0.1 meter, right?
0.01.
So you get 0.01 meters squared. Be careful of your unit conversions, okay? Next thing they tell you is that it goes around 20 times. So all you do is just multiply it by 20. So the total area would be 0.2 meters squared. So a lot of times, in fact, that's a great question. A lot of times what they'll do is they'll put a little n in here. The n means how many loops there are. So if we have one loop, it's just BA cosine theta. If you have 20, then it's B20A cosine theta. All right? How much time we got? 7 minutes? Okay. All right. I'm going to introduce you to this because this is totally brain numbing. All right? Heinrich Lenz, the other person that was coming up with these ideas, he figured out which way the current will go. You ready? You ready?
Yes.
All right, here's my loop. Heinrich Lenz said, this is called Lenz's law.
A circle, a circle.
And then
Here, I'll write it all out.
E and Z. Then
At the curves. It's a circle.
I think he just copied off the other
All right, I'm read it to you. It says, Lenz's law says, the induced current is such that the current's own magnetic field opposes the change in flux. All right?
Basically, it doesn't want to move, but you force it to move, right? Is that what it is?
Well, it ends up being that the current in a loop can only go one way or the other. Okay? Clockwise or counterclockwise, right? Through the loop. And it turns out that if it goes opposite to the way Lenz said, then it will violate conservation of energy. All right, it'll create energy from nothingness. I'll show you why in a little bit. All right? All right. And so Lenz's law is actually a way to describe how the current will go so that it doesn't violate conservation of energy. All right, here you go. Here's how it works. Okay? Here's my magnetic field. All right, now, first thing, do we have a closed loop?
Yes.
Yes, so we have an area. Do we have a magnetic field?
Yes.
Yes. Do we have flux?
Yes.
Because my area is this way and my vectors are pointing through, right?
So, it's a
So we have flux.
Max.
Okay, is the flux changing with time at the moment?
No.
No. So would we get any EMF?
No.
So would we get any current?
No.
No. Okay, so what we have to do is to change one of these. Let's change B. Okay? Let's say that the magnetic field is getting bigger with time. Okay? Magnetic field is getting bigger with time. Now hang with me. If the magnetic field gets bigger with time, where is my flux area? Just here.
Just a circle?
Just the circle part. We don't care about what goes on outside here. Is that clear? Just concerned about what goes on inside my flux area.
Okay.
All right, my B field is getting bigger. So my flux is increasing with time, right? So will we have an EMF?
Yes.
Yes. Now, my EMF is going to induce a current. I only have two options for current. Current this way or current this way. All right, here's the deal. The current will be such that it will oppose the change in flux. Which way is my flux changing? Is my flux changing to be bigger this way? Or is my flux changing so that it's changing towards this direction? So is my flux arrow through here getting bigger or smaller? Bigger. So it's changing that way. So in order to... what Lenz's law says is that the induced magnetic field inside here will try to cancel that change.
Where's the force?
No forces. Hang on. So my flux is going this way, and it's getting bigger. And we want to cancel out the getting bigger. My magnetic field's getting bigger. How do I cancel out this magnetic field this way getting bigger? I would add to it a magnetic field
The other way?
this way to cancel it out, right?
So the current...
So which way does the current have to go to give me this?
Counterclockwise.
Oh, yeah, counterclockwise on.
There you go. So there's my answer.
Oh,
So you're opposing the getting bigger, the change. What if my magnetic field was getting smaller?
Then you
then my magnetic field's this way but getting smaller, so I need to add more to it this way to keep it from getting smaller, right? So then my current will go the other way. Does that make sense? Okay. We will practice all of these next time because I just wanted to introduce it to you because it takes a while sometimes for this concept to soak into your brain. And I shall show you a little trick before you go. Hey, watch.
Move, magic, magic.
It is magic. All right?
Magnets of doom.
Okay, see this? Gravite, right?
Gravite?
Gravite.
Ah.
Right?
I know those.
Gravite.
It slows down. You see how it slows down in there?
No, it's an illusion.
She's doing her hair.
No, it's not an illusion. You can watch it go through.
It's just that the
A metal tube.
Or is it? They have some.
Looks like an elevator.
Oh my gosh, you guys are close. That was a book. I was
Oh my gosh.
Ah, connected. See? All right, you see?